Hello everyone! Today we're jumping into a real classic from the legendary Irodov problem collection. We're going to look at problems 1.87 and 1.108. Now, this is a puzzle you might think you know, but we're going to explore a really cool twist that makes it so much more interesting. It's a fantastic way to really nail down some key ideas in mechanics.
So you've probably solved this one before, right? A little block slides off a stationary sphere. You know the drill, you know when it loses contact. But what happens if we yank the entire sphere out from under it with a constant acceleration? How does that change the exact moment it breaks off? Well, that is the puzzle we are going to solve together today.
Okay, so first things first. Before we get to the accelerating case, we've got to have a rock-solid understanding of the original problem. So let's do a quick refresher on the good old stationary sphere. It's all about building that foundation. So here's the setup. This is Irodov's problem 1.87. Just picture a tiny object sitting at the very top of a perfectly smooth sphere. We give it the tiniest little nudge so it basically starts from rest and it begins to slide down. The big question is, at what exact angle, we'll call it theta, does it lose contact with the sphere and just fly off?
Now, if you've been through a mechanics course, this should look pretty familiar. First, you use conservation of energy, right? Potential energy at the top gets converted to kinetic energy as it slides down. That gives you its speed at any angle. Then you look at the forces. You've got gravity pulling down and the normal force from the sphere pushing out. And here's the key. The breakoff happens at the exact moment the sphere stops pushing on the body. In other words, the normal force N drops to zero.
And when you work through the math, you get this beautiful constant result. The breakoff angle is always the angle whose cosine is 2/3. That's about 48.2 degrees, by the way. This is a classic result in mechanics. You should definitely lock this one away.
Okay, so we've got our baseline. Now we're ready for the twist. We're leveling up to problem 1.108, where that sphere is no longer just sitting there. It's time to introduce a little bit of chaos.
And here is the game changer. The entire sphere is now accelerating sideways with a constant acceleration. Let's call it W0. The little body still starts from the top, but now the very ground beneath it is moving.
So what does this do to our nice, clean solution? Can we still use our good friend, the law of conservation of energy? The answer is a hard no, at least not from our usual stationary point of view. And this is a huge pitfall, so listen up. That accelerating sphere is pushing on the body, and the normal force is now doing work. That's a non-conservative force, and it messes everything up. We need a better tool.
And that better tool, that more powerful approach, is all about changing our perspective. Instead of watching this from the side like we're in a lab, we are going to jump onto the accelerating sphere itself. This is the key insight, and it turns a really tricky problem into something incredibly elegant.
By doing this, we're now in what physicists call a non-inertial reference frame. You can think of it like this. We're sitting on the sphere, and from our point of view, we're not moving, but the world outside is. Now, to make Newton's laws work correctly in our new accelerating world, we have to invent a new force. We call it a pseudo-force.
And here it is. This is the magic ingredient. In the sphere's frame, the body feels this fictitious force. It's equal to its mass times the acceleration of the frame, but, and this is the part everyone forgets, it points in the opposite direction. So if the sphere is accelerating to the right, our little body feels a force pushing it to the left. Don't forget that minus sign.
Okay, so with this new pseudo-force in our toolkit, the problem suddenly becomes much easier to handle. We can go back to using the work-energy theorem and a force balance, just like in the classic case. We just have to remember to include our new force in the mix. So let's set up those equations.
All right, the best way to tackle this is to get organized. This table is basically our roadmap to success. We're going to list every force acting on the body from the sphere's point of view. For each force, we need two things. First, the work it does as the body slides down to some angle theta. We'll need that for our energy equation. Second, we need its component pointing towards or away from the center of the sphere, the radial component. That's for our force equation. Gravity and the pseudo-force both do work. But remember, the normal force is always perpendicular to the motion, so it does zero work.
And that table lets us write down our two key equations. First, the work-energy theorem. The kinetic energy of the body is equal to the work done by gravity plus the work done by our new pseudo-force. See how it just adds right in? Second, the radial force balance. The net force pointing toward the center, which is the inward part of gravity minus the outward part of the pseudo-force, has to provide the centripetal force, mv² over r.
And just like before, we apply this at the exact moment of breakoff, where that normal force N becomes 0.
Now for the algebra, which is actually kind of neat. We've got two equations and two unknowns, the velocity and the angle. We want the angle, so we need to get rid of the velocity. So you can take that second equation, solve it for mv squared, and then plug that right into the first equation. When you clean everything up, it all simplifies down to this single beautiful expression for the breakoff angle, which we'll call theta naught.
But check this out. This is the really amazing part. When you go back and solve for the velocity of the body relative to the sphere at that breakoff moment, you get this. Now, does that look familiar? It absolutely should. It's the exact same relative velocity we found in the stationary case. How cool is that? The sphere's acceleration totally changes where it breaks off, but not how fast it's moving relative to the surface when it does. That's a deep and pretty surprising result.
So we've got our general solution. But any good physicist will tell you the job isn't done until you've checked your work. The best way to do that is with a sanity check. A more complicated general solution should always simplify back to a special case that we already know is true. Let's see if our new formula holds up.
And watch this, it is so satisfying. If we take our new general solution for the angle and we ask what happens if the sphere is stationary, well, that just means we set the acceleration w0 to 0. When we do that, the entire second term just vanishes. And what are we left with? Cosine theta equals 2/3. It reduces perfectly to our classic answer. It works. Our physics is solid.
Okay, home stretch. Now we just have to answer the second part of the problem. It asks for the specific breakoff angle when the sphere's horizontal acceleration is equal to g, the acceleration due to gravity. So we just plug w0 equals g right into our formula. The g's cancel out, and we're left with this much simpler equation to solve.
You can solve this equation numerically, and what you get is a breakoff angle of about 17 degrees. Now think about that for a second. Compare that to the almost 48 degrees from the stationary case. It breaks off so much earlier. And that makes perfect sense, right? That horizontal pseudo-force is basically pushing the body sideways, helping to fling it off the sphere much sooner than gravity alone would. So, what is the big idea we should take away from all this? It's the incredible power of choosing the right reference frame. We took a problem that looked really messy, and by just jumping into the accelerating system and adding one little pseudo-force, it became a straightforward application of principles we already knew. It really leaves you with a powerful question to think about. What other complicated problems, in physics or anywhere else, could suddenly become simple just by changing your point of view?